Let's study PCA. So why do we want to study PCA? Let's take a look at this demo. This is a visualization demo from Google's embedding projector built using TensorFlow. So let's change it to a MNIST database, which here it visualizes 10,000 MNIST images, and each image has a dimension of 784. And let's use different colors to label different digits. So now what you see here is a visualization by PCA using the top 3 PCA components. And these 3 components basically capture 26.3% of the total variance. Right, so PCA is the default method for visualization in Google's embedding projector over here. Right, so you can drag it and see the data in 3D space. And we can also view the data in 2D space, which you can just uncheck this. The third component, now we can see the top 2 PC captures 20.2% of the total variance, right? So you can also see the variance captured by individual components, and you can use, for example, the first PC and the third PC, right? So to visualize you can use different PC, right? So it's sorted by the variance, actually the eigenvalues for each pixel, right? So for each PC. So this is a visualization, and we can see that PCA is very useful in visualizing data to get some insights. So let's go back to the slides. So the idea of PCA is to rotate the data using some rotation matrix. And this is basically a change of the basis in the space. And we want to find this rotation matrix so that the new features in the new space are uncorrelated. So for example, here, our original space is described by x1 and x2, and we find a rotation matrix that can rotate the data into a new direction of u1 and u2, so that along these two directions, the features are uncorrelated. And then if we want to do dimensionality reduction, we just keep the dimension with the highest variance. So in this example here, may I ask you which direction capture the highest variance? So the answer is U1. Basically, this direction captures the most variance. Therefore, if we want to keep only one direction, we keep U1 and discard U2. And PCA was proposed in 1973. It's almost 90 years old. It is a fundamental linear embedding method. So PCA basically rotates to find the directions in data with maximum variance. So how do we find these directions? PCA to find these directions by diagonalize the sample covariance matrix, also called the scatter matrix. So this matrix is formed using all the input samples like this. So mu here is the data mean. That's the mean of all the n data samples. So subtract the mean means to make the data make the data after the subtraction to be zero mean, and this is called centering. We will look at the scatter matrix in more detail in the next session. So in PCA, we given data samples, we want to find the orthogonal directions. These orthogonal directions is defined by a rotation matrix U, or it's also called a projection matrix, that will capture the most variance in the data. And the solution of PCA is given by the eigenvectors of the scatter matrix S. And having this solution, we can obtain the PCA representation by using the projection matrix to project the input X to an output space Y. So this is also called transformation or mapping, basically map X to a low-dimensional Y. So given the PCA representation Y, can we obtain an approximation or reconstruction of X? So you can pause the video and think about it. So yes, we can obtain an approximation of the input X by using the same U to reverse map back to the input space. So we can use U to map Y back to X, the input space. And this is an approximation with actually the least mean square loss. So here we take a look at how this representation and reconstruction is working in the subspace. So let's look at representation first. Suppose we want to represent a face X. And using PCA, we can represent this face in k coordinates in the face space. So this is the first eigenvector, and this is a case eigenvector, and this is a data mean. So after we subtract the mean and then do the projection, we obtain a coordinate in the first direction, W1. And we do this for all the k directions, and we obtain k number of coordinates. So this representation means there's a k-dimensional space, and these are the coordinates in the k-dimensional space. So the subspace representation of this face basically becomes a point in that k-dimensional space. And we can, as we discussed in the previous slide, we can use these eigenvectors as the orthonormal basis vector to reconstruct the image using these coordinates. They are actually also the weights. Right? So basically, this is a mean image. That's a mean for all the samples. And this is a coordinate for the first direction. And this is the first eigenvector, and so on. So we basically have a weighted sum of the top k eigenvectors, where the weight is the coordinate we obtained in the subspace. And after summing this up together with the mean, we have a very good approximation of the input image. So here is an illustration of how the reconstruction performs when we have more and more eigenvectors used. So this is the reconstruction using just 4 eigenvectors. And when we use 200 eigenvectors, we can already see the face more clearly, right? So that 4, when we use k equal to 4, is more like a generic face, right? You can't recognize a person from that. But here you can already recognize a person. And when we use 400 eigenvectors, it looks, the reconstructed image looks almost perfect. So that is PCA. And let's look at the key ingredients in PCA. So we still do standard pre-processing, and the PCA basically construct a linear projection, a linear transformation from the input X to an output Y. There's only one hyperparameter, which is the lower dimension K, which is often determined by specifying the number of a percentage of variance to be captured, or directly specify how many pieces we want. And what we are learning, the parameter, is the eigenvectors, or the principal components. And basically, we obtain it by maximize the variance captured. So the optimal solution is given by the projection matrix projection maximizing the variance. And we can obtain the solution by doing eigen decomposition on the scatter matrix. So that is a basic introduction to PCA. In the next session, we will look at PCA in much more detail.